Okay, so in this video I'm going to be doing some harder proof questions, and the reason they're harder is because there's some additional reasoning that is required. In the previous ones it was just do the algebra, and at the end if you follow the rules you'll always come up with what you're looking for. These ones I've selected are much trickier, and I would expect them to be right towards the end of the higher paper. So it says here, prove that the product of three consecutive integers is always a multiple of 6. Okay, well let's just even think about what this question's even talking about numerically before we think about what's happening. So numerically, let's just try some of them out. Let's just pick three consecutive integers. Let's do 3, 4, and 5. And when we multiply these together, we're going to get 3 times 4, which is 12, and 12 times 5 is 60. Yep, that's clearly a multiple of 6 because it's 6 times 10. Well, let's try some big ones. Let's try like 11 times 12. No, let's not do 11. Let me try a different one. Let's go 10 times 11 times 12 like this. So I'm just going to do that on the calculator. Let's do 10 times 11 times 12. We get 1320. Let's see if that is indeed a multiple of 6. Yep, it is 6 times by 220. Okay, let's see what the problem will be if we do this one algebraically. Algebraically, you're probably going to want to do some consecutive integers. You might do n, you might multiply it by n plus 1, and you might multiply it by n plus 2. You probably might even do n plus 1, and n minus 1. That would also be 3 consecutive integers. But I'll try it with this one here, and let's just see what happens and see why we kind of come to a bit of a roadblock. Obviously, we don't need those multiplication symbols in between because we're just doing some things algebraically. Let's see what happens when we expand these brackets. I'm going to expand the second two brackets. That's going to be n squared plus n plus 2n, that's 3n, plus 2. We get n cubed plus 3n squared plus 2n. Right, well this doesn't show that it's a multiple of 6, because normally if it's a multiple of 6, we want to take 6 out as a factor, and we can't do that without making this thing inside here have some fractions. In fact, you'd have a 6th n cubed plus a half n squared plus a third n, and that doesn't guarantee that this thing is going to be an integer, because we're taking integers and dividing them by things, so that doesn't guarantee that it's going to be a multiple of 6. So we kind of come to this roadblock here where this technique is not going to work. Numerically, it doesn't prove it, it just shows that it works. So we're going to have to use some additional reasoning for this kind of thing. Well, let's just have a look at these three numbers that we've got here. And let's actually try and think, what does it mean for something to be a multiple of 6? I'm going to begin by talking to you about some multiples of 6. So some things we might think of, I don't know, we've got 6, 12, 60, 72. All of these things here are examples of multiples of 6. And what do they all have in common? Well, they are all, hopefully you can see this, they are all even, and they are all also multiples of another number. What number are they all going to be multiples of as well? They are all multiples of 3. So we're going to change this question. Rather than saying that it is a multiple of 6, we're going to prove two different things. We're going to prove that it's either even or a multiple of 2, and we're going to prove that something is a multiple of 3. If you think of any number and it's even and it's a multiple of 3, it must be a multiple of 6. So we can't prove that this is even or that this is a multiple of 3. So how are we going to do it? Well, let's just have a look at our three consecutive numbers. I'm going to pull down that 3, 4, 5. Okay, let's have a look at the 3, the 4, and the 5. Well, we just need to prove that this is going to be a multiple of 3 or a multiple of 2. Well, very clearly it is going to be a multiple of 3. It is going to be a multiple of 3. I don't like using that little multiply symbol. I'm going to say that it's definitely going to be a multiple of 3 because we're multiplying it by 3 at some point. And it's definitely going to be a multiple of 2, or an even number, because we're timesing it by 4. Anytime you multiply by an even number, think of any number and times it by 4, I guarantee it's going to be even. And it doesn't really matter about this 5 here. So we can tell this one is definitely going to be a multiple of 3 and a multiple of 2. So overall it's definitely going to be a multiple of 6. Well, does it work when we do it with the 10, the 11 and the 12? The 10, the 11 and the 12. Well, actually this time we've got two choices for the multiple of 6. The multiple of 2. We can see that the 10 is a multiple of 2, as is the 12. And the 12 is, this is going to get a little bit messy, the 12 is also a multiple of 3. Why don't I do this in a different way? Why don't I highlight them? So the ones that are multiples of 2 are these, and the ones that are multiples of 3 is this one and this one here. So what I'm getting at is that when you have 3 numbers in a row, at least one of them is going to be a multiple of 2. This one is a multiple of 2, and here these 2 are multiples of 2. And at least one of them is going to be a multiple of 3. If you take any 3 numbers in a row, it's definite that one of them is going to be a multiple of 3. So we just kind of need to express this in some language. So what I'm going to do is, if I have 3 numbers like this, let's say I have n plus 1, and n plus 2, we need to just explain at least one of these will be even. Exactly one of these will be a multiple of 3. Hence, their product will always be a multiple of 6. Squeeze it in on the page. It's not that clear to see, it's just the logic does work. You can see how this feels totally different to these questions we were doing here. It's less about algebra and it's more about the logic of what's happening. At least one of them will be even, at least one of them will be a multiple of 3, hence not at least exactly one of them will be a multiple of 3, hence their product will always be a multiple of 6. So this is a nice little trick to break something down, and actually this comes up, if you end up doing further maths, this comes up in a topic called proof by induction, which is in your first year. There's often questions where you have to show that something is a multiple of 15, and actually you need to show it's a multiple of 3 and a multiple of 5. So I'm going to try this question here that's going to have a similar kind of logic, and then I want you to have a go at this last question, which is a pretty tough, challenging one, but it uses the same ideas, there's nothing new. So let's try this one. It says, prove that n squared minus n is always even, given that n is an integer and n is greater than 1. So it's basically just saying you're only allowed to use whole numbers here, and it's got to be bigger than 1. So it could be like 2 squared minus 2, 3 squared minus 3. We want to prove that it is always even. Now there's a couple of ways of doing this one. I'm going to do method 1, and then I'll show you a different one that would also be accepted if it were in a GCSE exam. And I'm going to do method 1 that's most similar to what I've just been doing, okay? I'm going to start off with n squared minus n, and I talk to my students at A-level. I talk to them and say, oh, well, what could you even do with this thing? There's nothing, you've only got a few options in maths. You can either expand, factorize. There's not so much manipulation that you can do. So just do something and see if it leads to something. Well, I think when I see this, my mathematical common sense says, well, they've both got an n, so let's factorize by n and see what we have. So when I factorize by n, I get n brackets n minus 1. And this is the stage where I need you to think about what these two numbers are. How could we explain to someone what are n and n minus 1? Well, hopefully you might be using one of my keywords from earlier on. N and n minus 1 are consecutive integers. Now, because they are consecutive integers, this means one of them must be even. This means one of n, or n minus 1, must be even, as anything multiplied by an even is even. N squared minus n is always even. Now, I've seen this asked in a similar kind of way, and there's a different way that they would accept an answer to this. So we're going to just think about what is something that's called proof by exhaustion. You don't need to know this until you get to A-level, so I'm just going to put it in brackets. But we're going to do a proof by exhaustion. Now what this means is we're going to exhaust all the possibilities of what n can be. So n is an integer, but it's either going to be an odd integer or an even integer. So if n is even, n squared is even, because an even number times an even number is an even number, and n squared minus n is also even, because when you take an even number and you take away an even number, you get an even number. Now we're going to exhaust the possibilities by saying, okay, well, let's pretend that n is odd. Well, think of it, if you take an odd number and you square it, you get an odd number. 5 times 5, 25. 7 times 7, 49. If you do n squared minus n, if you take an odd number and you subtract an odd number, you get an even number. So hence, n squared minus n is always even. So this second method is just kind of using proof by exhaustion. Yeah, you don't need to call it that. It's just using logic and saying, well, if you look at all of the numbers that n can possibly be, the evens and the odds, you can clearly see it's only ever going to end up with an even. And you can use this logic of, you know, n is even, n squared is even. You don't need to prove that because that's kind of a given. That's something that we understand. And if you have an even number taken away an even, or an odd take away an odd, you do get an even. You can use this kind of logic. I probably prefer this one, but this is very elegant as well and would be perfectly acceptable in a formal assessment. Okay, so here's one for you to have a go at that uses some of that further reasoning that I've been talking about in this second video. It wants us to prove that any odd integer squared is always one more than a multiple of 8. Prove that any odd integer squared is always one more than a multiple of 8. Okay, let's have a look and see what we can do with this one. So we are going to take any odd integer. Let's say let n be an integer. If I say that I'm going to make it an odd integer, I'm going to get 2n plus 1, and I'm going to square it like this. And I want to show that it's one more than a multiple of 8. So let's square this bracket. And remember, you can do the double brackets if you need to, 2n plus 1 and 2n plus 1. We're going to get 4n squared plus 2n plus 2n plus 1. So we get 4n squared plus 4n plus 1. Okay, well, disappointingly, we can't just have that there's an 8 for this beginning part. It seems like we're showing that it's one more than a multiple of 4. So let's actually just do that bit because it could be useful. I've got 4 brackets. In fact, for these parts, yeah, we're going to say 4 brackets, n squared plus n plus 1. So this part, unfortunately, rather than showing it's one more than a multiple of 8, I've shown that it's one more than a multiple of 4. Well, let's go back to that idea of mathematical common sense. I've got this n squared plus n here. I wonder if I can factorize that and see if it tells me anything. So I'm going to get 4 brackets, n brackets, n plus 1 plus 1. Here we go. These two numbers here are also consecutive integers. So this exact logic that we had here of them being consecutive integers, these are consecutive integers, which means one of them must be even, which means you have 4 multiplied by an even number, which is something that's 8, hence it's one more than a multiple of 8. So we need to now just say n and n plus 1 are consecutive integers. So 1 must be even and a multiple of 2. As there is also a factor of 4. Any odd integer squared is hence one more than a multiple of 8. Now it's definitely harder to see. Let's just say that one more time. Clearly it's one more than a multiple of 4, but this section that we've got in here, either n or n plus 1 is even, which means if it's even, it's a multiple of 2. Multiple of 4 and a multiple of 2 means that this part here is a multiple of 8, so it is one more than a multiple of 8. It's a bit hard to explain, so use more words than this if you need to, but try and get your point across by showing that you know that this is even. It's really quite a similar style to what we looked at for this one, always being even n squared minus n squared plus n is also going to be even as well. So that's everything on algebraic proof. I will put some links in the description for you to go and do some more practice if you're looking for some. Okay, good luck. Found this video helpful? Then why not drop it a like and consider subscribing to my channel. This is the end of the playlist, but head to my channel's homepage to see what else I might be able to help you with. And as always, wishing you the very best for all your studies.